Hello guys, welcome to my YouTube channel. So let me introduce myself. I'm a metallurgical engineering graduate. My main objective of uploading this numericals on metallurgical engineering, the aspect of gate examination, is I want to prepare myself for the gate 2026. I want to crack the grade 2026 by preparing and uploading in the YouTube. Like, the best way to get the knowledge is to teach someone. So I believe in that, and let's be together in this journey. I'll be uploading couple of videos a week. I'll be first covering mechanical metallurgy numericals. So I'll be starting with the easy topic, composite materials. So let's dive into composites. So as we all know, actually I'll also upload the detailed notes on composite materials. I'll do a separate video on that as well. So let's see the numericals of composites. So as we all know, composites are the mixture of two or more than two constituents or phases which has properties different than individual element or constituents. So let's say A and B are two different elements or constituents which have two different properties. So if we want A properties and B properties as well in the same material, we use composites. So there are different types of composites, which are, for example, polymer matrix composites, ceramic matrix composites, metal matrix composites, and so on. I'm not going to explain in detail in this video about composite materials, but I'm going to explain the numericals which come in gate examination frequently. So let's see important formulas for numericals. Rule of mixtures. There will be a derivation for this. I'll be uploading another video on this derivation. So let's see the direct formula here. So imagine a composite experiencing a longitudinal loading. That means the load is along the fibers of the composite. The matrix and reinforcements are considered as fibers. So EC equals to EMVM plus EFVF. Here EC is elastic modulus of composite, EM is elastic modulus of matrix. EF is elastic modulus of fibers, VM is volume of matrix, VF is volume of fibers. So we have another relation called VM plus VF equals to 1. If one of the volume fraction is not given in the question, there is no worry. We can find another volume fraction using given volume fraction. Example, if the volume of matrix is given, then the volume of fibers can be found by VM equals to 1 minus VF. So in the same longitudinal loading conditions, we have another formula, the fraction of load bearing by the fibers. So when we load longitudinally to a composite, the fraction of a load borne by the fibers can be calculated by the below formula. Load fraction of fibers equals to elastic modulus of fibers by elastic modulus of composite into volume fraction of fibers. For the similarly, if we want to calculate fraction of the load borne by the matrix, we can use the below formula, that is Fm equals to Em by Ec into Vm. Now consider transverse loading, also known as isostress condition. Before we considered longitudinal loading, that is isostrain condition. The strains are equal, here the stresses are equal. So the load is given perpendicular in perpendicular direction. The formula is 1 by EC, that is elastic modulus of composite equals to volume of matrix by elastic modulus of matrix plus volume of fiber by elastic modulus of fiber. So the load borne by the fibers in transverse loading is given by the below formula. Fraction of fibers equals to volume of fibers by elastic modulus of fibers divided by the below formula is corresponds to 1 by EC, simply given as Vf by Ef plus Vm by Em. Similarly, for the load borne by the matrix, Fm equals to Vm by Em by Vf by Ef plus Vm by Em. There is another formula through which we could get a couple of problems in GATE examination, which is known as specific Young's modulus of the composite. It can be calculated by the given formula, Young's modulus by specific gravity. The specific gravity of the composite can be calculated by the below formula. Specific gravity of the composite equals to specific gravity of matrix into volume of matrix plus specific gravity of fibers into volume of fibers divided by volume of matrix plus volume of fibers. Now let's see a question which is given in a GATE 2019 examination. A material is made up of alternative layers of metals A and B, is loaded perpendicularly, that is transverse direction. If the volume percentage of B is 25%, the elastic modulus in gigapascals of the material is given. EA equals to 200 GPa, EB equals to 100 GPa. So as we know, the perpendicular load direction, which is known as isostress, 1 by EC equals to 1 Vf by Ef plus Vm by Em. Here the diagram is given, so if you see the diagram you can understand that what is meant by the transverse loading. The longitudinal loading will be up and down. So we've been given volume of B, that is 25%, which can be written as 0.25. So we don't know volume of A. We can get volume of A by the below formula, A plus B equals to 1. A is equals to 1 minus B, A is equals to 1 minus 0.25, and A we got the value 0.75. So now we can substitute the values in the formula to get elastic modulus of composite, which is 160 GPa. Now let's see another question. For the above question, calculate the load borne by the fiber and matrix in transverse direction. So as we previously looked into the formula, the load borne by the fibers is FF equals to Vf by Ef divided by Vf by Ef plus Vm by Em. As we have the values from the previous question, volume of fibers is 0.75, elastic modulus of fibers is 200 GPa, and the volume of matrix is 0.25, elastic modulus of matrix is 100. If we substitute the given values, we'll be getting 0.6, which is equals to 60%. So therefore 60% of the load in transverse direction is borne by the fibers. Similarly, load borne by the matrix, if we look into the formula, Fm equals to Vm by Em divided by Vf by Ef plus Vm by Em. So we have the values already given. if we substitute the values in the formula, we get 0.4, which is equals to 40%. So 40% of the load is borne by the matrix and 60% of the load is borne by the fibers. Thank you. In the next video, I'm going to explain in the longitudinal direction of the composites. So stay tuned. Thank you.